Okay, welcome everybody. So today is SLT Low 3. It's our pleasure to have Zhongtian speaking from Australia. It is 4 a.m. there, so make sure to show your appreciation with some enthusiasm in the chat. Okay, take it away, Zhongtian.
Thank you, Dan. Okay, so in today's lecture, I'm going to give a very brief introduction to algebraic geometry. And since we are now convinced that singularities is very important in SLT, and the technology we use to deal with it is algebraic geometry. And I will do this by computing RLCT in a very simple example, which is just this one. And I hope at the end of this lecture, you will understand the notion in algebraic geometry involved in SLT, and you're also convinced that computing RLCT is very hard. Also, you don't have to read Harshon to study SLT. And right, so this is the outline of this lecture. First, I will introduce the basic notion we need, algebraic sets and singularities. Then I will introduce the blowup of affine spaces and normal cosine singularities, then resolution of singularities. In the end, we will compute RLCT for that simple examples. And don't be distracted from all these words, and everything will be encoded in examples. That's why this talk is basic handwriting, and because a lot of calculations and examples. All right, let's start. So first, this is a definition of algebraic sets or varieties. We start with k polynomials in real numbers in d variables. Then the set of common zeros of this polynomial defined as point in Rd, because we can think of polynomials as function, right? We input points in Rd and output a number. And the set of all common zero of these polynomials is called a real algebraic set. All varieties. And in the whole talk, we'll focus on the case, because here we have k polynomials. But in this lecture, we'll focus on the case where k just equal to 1. Right, this is a simple example of varieties. It's just parabolas, and the defining equation will be this x squared minus y, and then the vanishing set will be point on the plane so that b equal to a squared. And this is the curve we have. The nice thing about this curve is that you pick any point, you zoom in, then you can see it's pretty much the straight line, right? It's pretty much the interval. And this is another example of algebraic set. The defining equation will be this y squared minus x cubed equal to 0. And you can draw this curve on the plane, and then let's have a look at this curve. It's different from the previous one because, okay, at this blue point, or everything except the origin, you zoom in, you can see this curve is pretty much same as the intervals. But if you look at the origin, you zoom in, and you can see there is a fundamental difference between these two things. And this red dot is a singularity in this curve. And yeah, you can see singularity appears in algebraic sets quite naturally, not like in differential geometry, you have manifold. Basically, you only have this type of thing. Right, this is another example, simple example. And in this case, the vanishing set will just be this course because it's points in the plane where either A equal to 0 or B equal to 0. And again, everywhere except the origin, locally this thing looks like an interval, but at the origin, it is different from the interval. But in this case, this bad behavior point is kind of easy to describe, right? It will just be intersection of two lines, they intersect transversely. Right, that's an example of algebraic set. Now, and we also see like which kind of point is special in this algebraic set. Then we can start to define what's called singularity. So we let Y be a real algebraic set defined by a polynomial. By definition, it's a set of points where you plug into F, the output will be 0. A point in Y is non-singular if you compute the Jacobian of this polynomial F and evaluate it at a point P. This is a Jacobian. And you evaluate each of this thing at P. And the requirement is that this is not equal to 0 matrix. All right, if a point is singular, if the Jacobian at that point is indeed the 0 matrix. So far, so good with this definition. Yeah, then let's go back to the example we have. Verify this definition reflects the intuition we had before. So in this case, we can, in this example, we first compute the Jacobian of F. Which is this. And let's take an arbitrary point in Y. Just remind you, Y is this parabola. Then we can see the Jacobian of F at each of these points will just equal to -2 times A1. Since there is always a 1 in the second entry, we know this is never 0. Hence, every point in Y is non-singular. Good, this deal with the non-singular case. Let's have a look at whether our intuition is correct in the singular case. Again, for this polynomial, we first compute its Hessian, its Jacobian. (3x squared 2y). And for point, except away from the origin, we can say that the Jacobian is not equal to 0 matrix. But for the origin, then you know that you plug in 0, 0 to x and y, then we know the Jacobian is 0. So we know origin is the only singularity of this curve. So far, so good? Yeah. Right, then same thing happened for this one. You can say the origin is the only singularity of this variety. Good, we have algebraic set and the singularities. Now we can start to introduce the main notion in this lecture. Blow up of a affine space. So again, we take a real affine space, which is the Euclidean space Rd, and we pick a number R, integer between 2 and d. Then we can define a algebraic set, which is the vanishing set of this coordinate function. So this set will consist of points in Rd, so that their first R coordinate vanish. For example, if we take R equal to D, then this set will just consist of the origin, because every coordinate vanish. Then the blow up of Rd with center V is defined as the following. First of all, it's a subset of this product space. It's a product of Rd and P R minus 1. And then I will tell you what's this space later. First of all, let's write down this definition. We take the set, because this is a product space, right? Points there will consist of tuples. The first coordinate will be points in Rd, and the second coordinate which will be point in this projective space. This P is called projective space. The condition is that X is not sitting inside the center. And then we take the closure in this product space. From now, we just know each point in first we take the set, which is a subset of this product space, and then we take the closure. Now I will tell you what is projective space. So the idea is that this projective space parameterizes the set of all straight lines through origin in Euclidean space. So in order to make that intuition right, we can define it in this way. So you take the affine space R and delete the origin. Then you quotient out a equivalence relation, which says 2 points in the affine space are equivalent if and only if one is a multiple of the other. This captured the idea of that this space parameterizes all straight lines through origin, right? If you take 2 points in the affine space, you identify them as long as they sit in the same straight line through the origin. Right, and then we write coordinates for points in projective space using this notation, where because we know this, now this is an equivalence, each point is an equivalence classes. Like 2 points in the same line should be the same. So this just means these 2 coordinates are equal if and only if in the affine space, these 2 points are sitting inside the same straight line. Yeah.
So they use these colons versus commas. It's just a notational thing defined by this bottom sentence.
Yeah, yeah, just notation. Yeah. So this usual thing, this a comma ar, this just mean the points in affine space. That's our usual notation. But in projective space, we change to this notation, kind of to try to reflect the point that this is an equivalence class. If I give you two coordinates in the projective space, even though each of this number A1, A2, AR, and B1, B2, BR, they are different. Each of these tuple are different, but they might be the same in the projective space. Take 2 points, go back to the Euclidean affine space, and check whether they are on the same line or not.
I actually also have a question. Sorry, just about the definition of BVRD.
Yeah.
So we're taking like the way I'm thinking about the space is it's a vector in RD combined that isn't inside the center, and it's like one of these lines that's in the center, and then we're taking the closure, and in my head, like if I imagine taking the closure, it seems like the closure would be we just get rid of the restriction that that the vector x isn't inside the center. Is
yes,
that right? Or
yes,
so,
that's right.
So what's the condition even doing then? I'm kind of confused.
Yeah, well, say if you are right, taking the closure, we will include points in the center, right? But let's have a look at this set. If you are away from center, each point in RD, you just associate it with 1 point in P in the projective space, right? Which is a point already decided by your point X. If you pick X, stay away from V, and then the corresponding point in the projective space is determined. But what happens if you take a point in the center? For example, if we just take R to be D, the center will just be the origin, right? If you take a point in the origin, then this notation will not make sense, right? Because we have to delete origin.
So the idea is that the direction in V is determined by the point in RD, like it's the same x axis.
Not in V is determined by the point. Not in V is determined by x.
For points not in V.
Yeah, for point in V, we don't have any restriction on this point on the project space, right? Taking the closure will correspond to that. You add point in V to the space, and also the corresponding part in project space will just be the whole space. There is no particular one you can choose. It's not determined.
Okay, thank you.
Yeah. Great. When R equal to 2, then this will be the set of all straight lines to origin in R. Yeah, if R is equal to 2 and our center V is the origin, what we do is for each point outside of the origin, we will attach to it its direction, right? That's a point in the projective space. But at origin, there's a lot of direction we can choose. Basically, we will just use the whole the corresponding thing in projective space will be the whole space, whole projective space. Okay. Sorry. Great. Yeah, this is a point you make by taking closure. Just this simple product will add to the set.
Is there any difference between P1 and S1? Like, does the additional structure over the sphere?
Oh yeah, P1 it has the same topology as S1, I think.
You're identifying opposite points.
Yes.
Yeah, okay.
Right. Then if you take this as your definition, you can show that we have a closed form for this blow up, which is the following. Now, if I just write this just means any point in X and any point in the projective space. Unlike the definition, the point in the projective space is determined by X. Now it's not just arbitrary pair. I'll put on constraint here, which states that Xi times Yj equal to Yi times Xj for all Ij equal to 1. Right, you can show that this is equal to the blow up in our definition, and we will see this in examples. And basically, we'll work with this definition because, yeah, it's just explicitly describe what is BVR. Now we focus on the case D equal to 2 and R equal to 2. Which means the center will just be the origin. Then we know that by our definition, this blow up of two-dimensional affine space with center origin is this as a set is this set. First, you take the first coordinate, you take a point in the affine plane. And second coordinate parameterize things in P1. And the defining equation will be X times W equal to Y times Z. So now we take this as our definition for blow up. Now we notice that there is a natural projection, right? Because this thing sits inside the product space. We can just take a point in the blow up. And just read its first coordinate, which will be a point in R2. So let's have a look at the pre-image of this map or the fiber of this map. You take a point. If it's not the origin, not in the center, then without loss of generality, we can assume just say B is non-zero, right? As long as this is not origin, one of this number is non-zero, assume B is non-zero, then we can compute the pre-image of this pi at this point. So the pre-image will be first, the first coordinate is determined, right? Because the projection we project the first, we just read the first coordinate and it's equal to this point A and B. And then the equation become AW times equal to B times Z. And this is the same as AB. And so Z, because AW equal to BZ and B is non-zero, we know Z equal to A over B times W now. So and now there's no constraint anymore. So W can be
The W jumps in? Why keep the W? I mean, these are homogeneous coordinates. You just get rid of the W.
Oh, yes, yes. I will do that in the next step. So
Oh,
yeah.
sorry.
Yeah, I want to do things like step by step. Otherwise, but there's no more constraint, and then because we know points in the project space, this coordinates are the same if they are just differ by a scalar multiple, and this W is 1. We can get rid of it, right? Simply because this is just equal to W times this just equal to W times this. So these two are the same, we just replaced here. Then, as you can see, the pre-image of this point is just one point in the product space. The first coordinate is determined by the point, and hence the second coordinate is determined as well. So you take a point in the space in the plan, and you associate it with the direction of this line, with this line, with the direction of this line. You take a point, then you know this point and the origin will determine a line, and that's a point in the P2. That's a point you take for the second coordinate. Make sense? Any question? Sorry?
You go back to the previous one?
Can you go back to the previous slide for a second?
Yeah.
Okay, thanks.
Yeah. So our intuition is right, like take a point where there's only one point associated in P1 if we are not at the center. Indeed, if we restrict to if we restrict the domain of pi, if we just look at point in this set, like stay away from the center, then these two spaces are the same. Anyway, now let's look at the pre-image at the origin. Then we can just compute. This will be point in this product space, satisfy this relation. Then this is always true, then there's no constraint. So this will just be all points of this form, and this will just be a simple product with a 1 point space, product with P1. And we can identify this just with P1. Any question with this calculation? Yeah, so at the origin, the pre-image will be a copy of P1. Yeah, one intuition of this blow up is that why we will introduce this after singularity is if we have a singularity like this in the plan, and the blow up just means you pull apart this, you pull this curve in the up direction, and you will get things like this. And because in the plan, when at this point is it's bad, right? We have two tangent vector, right? We have two choices of tangent vector. After you you apply blow up, everything away from the origin is fine because there is a unique direction attached to them. But at the origin, because we know in the blowups, in the space of blow up, at the origin we have a copy of P1 there. So then we can separate these two directions. That's kind of the intuition of blow up. Okay, that's all. That's all the definition. And now we look at blow up from an algebraic point of view. Yeah, like
can I just ask you
yeah.
to go back from the start of the blow up and walk us
Yeah.
through it at a high level?
Yeah. Yeah, so the high level thing is you take the affine space, and the blow up just mean if we take the center just to be origin, then the blow up associates each point outside the origin a line, right, determined by the point. Let's just do P2, PP1. Let's just do P1, right? So if you have this blow, we have R2, and for everything except the origin, we take a point here. We know this point and the origin, they will determine a straight line, right? And a point in P1 is a straight line. Then we will associate this point with this particular straight line, right? But if we look at the origin, if we are at the origin, then there's no unique line is determined, right? So for in the origin, we put the whole P1 to it. And this is helpful because if we have a singularity, say like this one, again, away from the origin, each point we only associate with one point in P1 to it, right? This corresponds to there is only one tangent space, tangent vector. The tangent space is dimension 1. But for this singularity here, there is a two choice of basis for the tangent space, right? This
is going to involve a second step where we like shift the origin to be located at the singularities when we actually
yes, we need to do that, right? We introduce blow up to deal with singularity, and we want to blow up point which are singular points. Yeah, the thing about this geometrically require a little bit thought, but as you can see, it's okay. But now I will introduce you can do things from algebraic point of view, which will be more acceptable at the first time, I think. Right, the setup is again we take a real polynomial just in 2 variable now, and then we keep doing this. F is a real value function. We plug in point, we output a number. So if we do blow up on R2 with center being the origin, the blow up is not just the space BV R2, right? It's also this projection here. If we do blow up, we will have not only this space, also this map. And now we're just pre-composing this map to F, then we will obtain a real value function on the space. Since we already assume the center is origin, I'll just use O stands for origin here. Right, so after pre-composing, we will get a map. So the first step, you start from the blow up space. You do projection. You goes to the affine space. Then you can apply f. This is how we get a real value function on the blow up, given a polynomial. So now our goal is to compute this function. And from that, let me remind you definition. This is a definition of the blow up. And one nice property about this projective space is that P1 is covered by 2 copy of R2. The way to see this is from definition, we know P1 is this, where the constraint is just Z and W is point in R2, but delete the origin. Right, this is P1 by our definition. And we can partition P1 into, not partition, we can cover P1, we can write P1 as a union of 2 things. The first thing is this. Let me do this. This is, we can write P1 as a union of 2 things, and I will tell you what is UZ and UW. UZ will be point in P1 so that Z is non-zero. The first coordinate is non-zero. And because we know two coordinates represent the same point, if only if they are different by a multiple of the other. So we can, because Z is non-zero, now we can divide Z. This is the same as this. And there is no constraint on W. So W will just in R. And again, first coordinate is fixed, second coordinate is free. We know this is same as just R, right? Same thing for this UW, it will be point in P1 so that the second coordinate is non-zero. Then we can divide the second coordinate. And there's no constraint on that. And again, this is the same as real line. So given P1, we know it can be covered by two real lines. So far, so good.
Wait, can I ask a question which involves hijacking the camera? So I've drawn a little picture on the whiteboard of what I think is happening. So P1, I'm imagining it as this little like black semicircle with like 1 point sort of not included. So like every line, if the origin is here, every line through it intersects this semicircle at least 1 point. And I'm thinking of like UZ as sort of being this like red region. So including this end, but not including this end. And then UW as being this blue region. Is that right?
Yeah, it's hard to see from here, but
yeah, or actually is UW more like not including this point in the middle? Maybe. Oh no, I think UW is like.
yeah,
Oh
maybe,
yeah, I think UW is not including this point, like yeah. So I guess UZ is excluding horizontal lines and UW is excluding vertical lines. Okay, all right. Thanks for the digression.
Yeah. Wait, what? Right, because now P1 is covered by two real lines. now then they blow up as a subset of this space. It will also be covered by two things. The first thing the first one is this. Where the defining equation again is xw times yz, but now we add one more, w is non-zero. And we can compute this. Again, because w is non-zero, you divide w. Then you drop, then the constraint also become x equal to y times z over w. Now this, you can drop this coordinate. Then we will get x, y, z over w in R3 now, where the constraint is this. And this suggests that this set is the same as a copy of R2 because of this. We take R2 and I will use ST for coordinates on R2, and we will have a map ST goes to, again, let's look at this relation here. This just means the first coordinate is a product of the second coordinate of the rest of the coordinates. So we'll just let this point send to ST. And this is an isomorphism, meaning these two are the same. So far so good. We can identify this set just with this affine plane, right? Because this relation tells us the first coordinate is already determined by the rest of these two. Right. Then same thing happen for another copy. If we take z is non-zero, again we plug in the definition, add one constraint, they be non-zero. Then we can divide z in this coordinate. We will reach this set in R3, but the second coordinate is determined by the first one and the first coordinate and the third coordinate. Then we can identify this set with a copy of R2. Again, in this R2, I will use U and V as our coordinates. And this identification will just be, I take a point in R2 and it will goes to this triple. Like the middle one is a product of the first coordinate and the third coordinate. So by doing so, we know that the blow up is covered by two affine space. One is this, the other one I use SD and ST as coordinate, and the other I use UV as coordinate. Now we take this projection map, we can restrict it to each of these affine cover. Then I will use this notation, denote pi restrict to this affine space. First, we have this identification, right? This affine space is identified with this subset of blow up, and this sits inside the blow up, which just require W coordinate to be non-zero, and then we can apply projection. This means we take ST, it goes to this tuple, and then project to the first two coordinate. And same thing happen for UV. We take UV, we goes to UVV, and we project to the first coordinate. So now what we have done, we start with the blow up, we cover it by 2 affine space, and we compute what's its projection on what's its projection map on each of these affine space. Our goal is to compute this function, and we do so by consider it's on each of these affine space. On this R2 with ST as coordinate, F compose pi will be this. Again, we first apply pi, then apply F. So we take ST, apply pi on ST, we will get ST comma S, and apply F to this point. And same thing for the other affine cover. You take a point, first apply this pi UV, you will get U comma UV, and then apply F to it. So now we compute this function on each of these affine space. Right, so if I give you a polynomial, you take the blow up, the effect of blow up on this polynomial will be you just substitute ST to X and S to Y in this coordinate, and in another coordinate you substitute U for X and UV for Y. Let's do this in an example. Let's consider this polynomial, and this is a curve. This is a algebraic set. It determines this curve, and you can see it has a complicated singularity at the origin. You can also do this, just use our definition. You compute the Jacobian and argue that origin is the only point where Jacobian and this polynomial vanish. Then we blow up R2 with the center being origin. Then we have this map. And we know that what we did before is we cover this by two affine space. Well, it's not strictly like union. Like these two are different things. This union just means we need to glue them, but we won't talk about that here. But we just treat them. These two is this blow up space is covered by these two. We look at F. We look at F compose pi on each of these individual coordinates. So on the first coordinate, from our calculation, we know that F compose pi is F compose pi restrict to the first coordinate, which is F. You substitute ST for X and S for Y. And this will be ST to the fourth minus ST square S plus S cubed. So on this affine cover, F compose pi is this polynomial. Then we can draw the picture of this. On this coordinate system, ST on this affine space, F compose pi give us a algebraic set, which is this one. It has two components. three components, you take this is a curve, it determines. And you can show that if I take the you can show that this line here, S defined by S cube equal to 0, is the pre-image of the origin. And this two smooth curve is the is a closure of the pre-image of the original curve delete the origin. And we usually call this one, this pre-image of 0, we call it exceptional curve. And we call this smooth part strict transform. And the union of exceptional curve and strict transform is called total transform. Are we happy with this picture, this calculation? How we get this polynomial? Basically, we first compute pi on each of these coordinates, then just do this composition. Yeah, similar thing happened for on the other affine cover. In this coordinate f compose pi, we do the same thing. We just substitute u to x and uv for y, and we will get this polynomial here. And then we plot the graph, and this part is the this part is the algebraic set determined by this equation, and this smooth part is the algebraic set determined by this polynomial. Right, this is a general picture we have. We start with this polynomial, and this is the algebraic set, has a bad behaved singularity at the origin. Then we apply blow up, we will have a map. This means we have a map pi, and on each of these two coordinates of a blow up, we know our variety will become our algebraic set will become this thing, this curve, and on the other chart it become this set, and again we still have singularity here, but this singularity now is not so bad, and we call them normal crossing singularity. Are we happy with this example here? Sorry, I can't hear you. Can you use the mic?
You call it's normal crossing, but what is it crossing? Haven't we?
Oh, yeah, I will define this normal crossing in the next step. This is just a intuition tell you that after you apply blow up, the singularity become simpler.
So I have a question. Sorry, I don't know if this makes sense, but in the original space, right? If I look at that little bow that's tied up at the origin, right? There are like, I count 6 lines coming into the origin, right? And if I look at dots you've drawn, I'm seeing 5 dots. And I'm wondering, so in the ST coordinates, it looks like there's this, there are these asymptotes, right? Where like you're approaching, like as t goes to infinity, s goes to 0, and as t goes to minus infinity, s goes to 0. I'm wondering, do those asymptotes count as the 6th crossing, or am I just like doing weird numerology that doesn't actually make sense?
Yeah, I
Like you only need 5 crossings.
Yeah, I think it. Yeah, why you have 6 cosine here? Like it's
You have 6 things coming. Like if yeah, you've got like 6 lines coming out of the origin,
Mhm.
right?
right.
But maybe that's not. So Matthew Ferrugia Roberts in chat seems to think maybe it's only 5 crossings. So I don't know if I'm counting the right thing even.
Yeah, it would make sure you have to.
One. Yeah, like I think like this one counts as 1. Right. Like you have 2 lines here, but they are they should count as 1, right?
Well, why doesn't
I think there are 3 because yeah, they're tangent between going through the origin.
Yeah, like I never thought about this interpretation. Just normally I do is you compute it and
Yeah, the tangent is horizontal.
Okay.
3, not 6, right? Yeah, I agree.
Right. So,
Oh, so it's 3 there and 3 there.
yes.
And that makes 3.
So,
Oh, okay.
so just to confirm, are these 3 on the left and 3 on the right identified? Well, 2 on the right plus the point at infinity. Is that correct?
can you repeat the question? What is correct?
So there's these 2 charts, right?
Mhm.
Sorry, I
Yeah.
just came in, so I might be missing some context. But you have 3 points on the left, and on the right you have 2 points plus potentially something on infinity. Are these 3 points identified under the gluing of these 2 charts, or not?
Yeah, that some of them. Yeah, like there is a gluing. Like some of them I identified. Yeah, but we don't worry about that. We just
Yeah.
look at them at each of these coordinates. So yeah, so far we just look at them at different coordinates and we compute it is what it is.
Right, but the question is, are there 3 points in total, 5 points in total, 6 points in total, or
Then yeah, I don't know the answer. Then you have to be careful about the
I
gluing
think
thing.
there should be 3 too, yeah, because
Try to think about
like
it,
if you have, yeah, it's just that tangent directions make sense to have 3.
yeah,
but
my guess
maybe
is
somebody can
3.
confirm or deny. Dan?
All
right.
The chat thinks
It's a distraction. We'll go on. Dan thinks it's a distraction.
sorry.
Right, now let's define this normal cosine. If we take a real polynomial in d variables, then f is a normal cosine polynomial if for each point in the Venetian set, there exists a coordinate chart u, y, such that f in this coordinate is just a monomial. Where this k just non-negative integer. Right. Then how to say this orange point are normal cosine singularities? I'll do example for, say if we are at just one of these points, say origin, we apply a change of coordinate. Phi, which sends u to u and v to u minus v plus v cube. And this is my new coordinate. And this is a change of coordinate because when you compute the Jacobian, this will equal to 1, 0, 1, minus 1 plus 3v squared. And this is invertible around origin. Right? Then if we apply this change of coordinates, we know f in this coordinate, in this y coordinate, will just be y1 to the cube and y2. So this tells us this point is normal cosine because we can find the coordinate so that this is a monomial. You can see from the picture, you zoom in, you will say like around this point, it will just be a straight line intersect with this. Again, if we just think about the set, this will just be a straight line intersect with another straight line in this transverse way. I put this squeezy here is just because, yeah, as a set, they are the same. I think that's what we just don't care about this. I'll skip this. Yeah, we can do the same thing for each of these points, and you can check they are all not. You can always find the coordinate so that f is monomial in that coordinate. And the full calculation will be on the notes. Okay. Yeah, we can do the same thing for f on another chat on another coordinates, and it's also a normal cosine polynomial. Right. So let's revise this example. We start with the f with a complicate heat singularity. Then we apply a blow up. Then we end up with a situation that in each of these chart, our f is normal cosine polynomial. Now it's time to introduce this Hironaka's theorem, which is the resolution of singularities. Again, we take a polynomial in D variables. Then we can apply a finite sequence of blowups. By applying a finite sequence of blowup, we can obtain a proper birational map G. We obtain a map G from Wn to the base space, such that the blow-up space can be covered by charts, and in each of these charts, our f is a normal cosine polynomial, and the determinant, the Jacobian of this, the determinant of the Jacobian of this G is given by a monomial. Yeah, this is a like oversimplified version, but it will do. So in this example, right, we take just one blow up. We are in a situation that f on each of these charts is normal cosine, and on each of this chart, the Jacobian of pi. Now in this case, our G will just be pi. The Jacobian of this pi is a monomial, right? Because you can compute it. Right, that's a theorem we'll use to compute RLCT. Before computing, we need to define it. The definition of RLCT is the following. You take a polynomial in D variable, and you pick a complex set. then the RLCT denote as this is defined as the, okay, you form the zeta function. This will, the zeta function, this will be a function on the complex plane, and the RLCT will just be the absolute value of the real largest pole of this zeta function. Right. How do we compute this? We will use the resolution of singularities. So we'll first apply the theorem, which means we do a finite sequence of blowups. We'll get a space Wn and a map G, so that Wn is covered by charts, and in each of these charts, Fg is a normal cosine, and the determinant of the Jacobian of G is a monomial. Step one, we compute all this blow up. Then step two, we will compute this integral. We can do a change of, because G is proper, so this equality holds. And we can cover this because G is proper and stays compact, the pre-image is compact as well. Then it can be covered by, it has a admitted finite cover.
Zhongtian, what does
Yeah.
proper mean?
Oh, proper mean the pre-image of compact set is compact.
It's a real.
Proper is it's a relative way to talk about compactness. So
Yeah.
really every time you hear proper, just think compact. But some of the definitions are a little more subtle.
Yeah. Now we can cover this pre-image of C by UI, right? And we know from the theorem in each of these Y coordinates, F compose G is normal cosine, then we can apply a further change of coordinates, makes it to be monomial. And again, because we do a further change of coordinates, we have to multiply. Before doing that change of coordinates, we know this determinant of a Jacobian is also a monomial. And because we apply a further change of coordinates, we'll multiply the determinant of that coordinates here, which is BU, BY, sorry. And because we are evaluate integral on different chart and glue them together, we need to multiply a partition of unity. Then this integral will just be this. Then you can say that the pole of this function will be the same as pole of this one. For in each of UI, pole of this one. Yeah, so pole of our original function are exactly the poles of this function. And again, we can evaluate this one. Right, this is just a integration. Then we can say the pole will appear when the denominator is 0. So for J equal 1 to D, this means KJ Z plus HJ plus 1 equals 0. And this means Z will equal to minus HJ plus 1 over kj. So these are all the poles, and the RLCT is the largest, the absolute value of the largest pole. So RLCT will be, because there's a minus sign, so we take the minimum. So on each of these charts, we can find the minimum, we can compute this number k and h, and then we take the minimum. Then we do this for each of these ui, then we take the minimum over all ui. That will be the RLCT. Right, now let's, because of the time, I will not write this I will not do this calculation now. I will just show you how it works. Right, now we are trying to compute RLCT of this
There's
thing.
there's a question in the chat from Alex about the intuition behind the RLCT. Maybe they should wait for Dan's lecture. So okay, so now we just accept it as a thing.
Yeah, that's a definition, and we know how to compute it using resolution of singularities. Right, I think like next lecture, SLT high will talk about that, I guess.
Yeah.
Now to compute this RLCT, first we know origin is a singularity, and we blow up R2 with center being this origin, right? Then we obtain this map, this pi1, and we did this before. Like, then this blow up space is covered by 2 affine space. On the first affine space, we know the projection pi is given by this map. You take the x1, y1, and you map it to x1, comma x1 times y1. And we know how, then we know f compose pi restrict to this coordinate will just be this polynomial here, right? We just plug x1 to x and x1 times y1 for y. Then we will get this polynomial. Then we can plot this polynomial, and you can see this is not normal cosine at origin. You can see from the picture, and or you can just say it does not satisfy the definition. On the other chart, we do the same thing. Our f will become f compose pi will be this polynomial, and we can plot the graph. And this is normal cosine, right? For each point, it's locally defined by a monomial, right? Locally, it's like a straight line at each point. So on this chart we're fine, but we have to deal with this part. Again, we apply another blow up at the origin. Then we do the same thing. We cover the blow up by 2 affine space, pi to R2, and on first R2, the projection is given by this map. This is a formula for projection. Then we can compute our polynomial on the first coordinate. We do the same thing. We can plot it, and you can see it's normal cosine, right? Each point on this curve looks like just an interval. Then on another chart, we do the same thing. We compute the polynomial on that chart, which is this one, and we plot it. And this origin is not normal cosine, right? For in R2, the normal cosine mean is locally defined by monomial, but in R2, it will just be intersection of 2 lines instead of 3, right? So this is again not normal crossing. Then you do the same thing again. You blow up at the origin and compute pi and compute the f on each of this chart. Then you can draw the, then you can get, then you can conclude that you will get normal crossing polynomial on each of this chart. You can see each of the singularity, they are normal crossing. So after we do like 3 blowups, we get then we reach a situation that every singularity is normal crossing. This is what this is the summary of what we've done in this example. First, start with R2, we do 1 blowup, and in this chart, it's in normal crossing, it's fine. So we look at this chart, we do blowup, and in this chart, now in this chart it's fine, then we do blowup on this chart. Finally, we reach a situation that on this 4 chart, our F is normal crossing. So because we do 3 blowups, so I use W3. W3 is covered by this 4 chart, and on each of this chart, we know F is normal crossing, and we can compute G. On this chart, we only do 1 blowup, then G will just be pi 1, and it's given by this, and we can compute the determinant of its Jacobian, and we know F is of this form, then we can rate K and H, where K is 2, K1 is 2, H1 will be 1, and K2, because the second coordinate is, this is non-vanishing, so we can do a change of coordinate so that this will just be y2 squared. So the K2, basically K2 is 0, and H2 is 0 as well. When K2 is 0, we will think about this as arbitrary large. So we pick the minimum one, which will just be 1 plus 1 divided by 2 is 1. Then we do same thing for this chart. Now in this case, the G will be composition of pi 1 and pi 2. Right now, G is a composition of pi 1 and pi 2, and we compute this, we'll get a formula for G. Then we calculate the determinant of the Jacobian, which is this monomial. And also in this chart, we know what's F. And in this case, K1 is 3 and H1 is 2. K2 again is 0, H2 again is 0. And you take the minimum one, which again is 1. Do the same thing for next chart. Now we are here. Now we are here, and we do 3 blow up to get this chart. So now G will be composition of pi 1, pi 2, and pi 3. Now we compute what's G look like, and it's a composition of these 3. Then we compute the determinant of the Jacobian, which is this monomial. And we also have compute that on this chart, the polynomial will look like this. Then the polynomial is this one on this chart. Then in this case, K1 is 6, H1 is 4, and K2 is 3, H2 is 2. Then we take the minimum one, which will be, this one will give us 5 on 6. This one will give us 3 on 3, which is 1. So the minimum one should be 5 on 6. And the do same thing for the last chart. Then we get the RLCT, which is the minimum among all this number, which is 5 on 6. So the RLCT of this curve is 5 on 6. Sorry about the rush for this example, but all the calculation details will be on the notes. And that's all. And you can see even for such a simple curve to compute RLCT takes a lot of effort. So that's the conclusion of this lecture. So any question now?
How many blowups do people do in practice? Like, how deep does it typically go? Like as deep as you like, but like, okay, so for real world systems or in practice,
It's
Nobody
impossible.
in history has ever done blowups for a real world system.
Yeah.
What do you mean? I mean, okay, so the 10H networks for which the RLCTs are known. I don't know exactly the depth of that in the Aoyagi Watanabe paper, but it's 60 pages long.
Was it done by hand?
Yes.
Okay.
In principle, you could do such things automatically.
yeah.
So for example, that paper probably with sufficient effort, you could automate that. But I mean, it very quickly explodes.
So I guess maybe general question for you, Dan, is it seems RLCTs to compute them for large networks is intractable. And I don't know if we know that for sure, but I assume we sort of think that. Could you say a little bit more about your hopes about what we would want to compute in practice? Yeah, are we doing approximations? Yeah.
Yes, maybe Edmund can also comment, but I would say there are two parts to that answer. One is you can always estimate things. So there's theoretically computing RLCTs by blowups, but there's also procedures for estimating it, and some of which Watanabe has written about and we and others have implemented. And the question of whether they scale or not is open, but there's some recent evidence that, for example, using things like SGLD or just techniques that don't require stochastic gradient Langevin descent, or just using methods that don't require approximating the posterior at all, you might get estimates that are bad but useful. I think it's highly unlikely we'll be getting estimates of RLCTs of neural networks in 1,000 or 1,000,000 dimensions to 5 decimal places. I don't see any path to that, except through the second component to my answer, which is here's the thermodynamic intuition is very useful. So why do physicists care so much about critical phenomena? So in the context of critical phenomena, so Jesse mentioned scaling exponents. There's like alpha, beta, gamma, delta. Now, some of those are easy to compute or measure rather, right? You measure them in the lab. Some of them are impossible. You're never going to actually measure those, but you have equations that tell you how to compute the ones you don't know or can't measure from the ones you can. And the existence of those equations is a consequence of you being at criticality. Okay, so the idea is that if you have a lot of phase transitions in your system, those phase transitions are special configurations at which certain quantities fall into algebraic relation. And the hope is that because you can compute some of them easily, then you can infer others.
Right.
So if we go back to my talk, I talked about the critical data set size.
Right.
It was a ratio of differences in RLCTs to differences in energy. You can compute energy. That's just loss. You can compute critical data sets. If you just look at your graph and you see where something happens, right? So you can infer from that, from the phase transition, the difference in the RLCTs. That's super cheap. So differences in RLCTs probably are really cheap. Like absolute values may be very difficult.
Thank you a lot for that answer. I think that was very insightful. Next question.
What do we know about the location of the largest residue, or do we not care of the zeta function? Inspect. Oh, we don't have audio? No.
Zhongtian muted or?
I can't.
Yeah,
Oh, now I can hear you.
okay.
Did you hear the question, Jonathan?
No.
Oh, the question from Nathaniel. What do we know about the location of the largest residue, or do we not care? I guess there are other, just about maybe other invariants besides the RLCT, like what other features of the zeta function might be important?
Multiplicity.
Yeah. Thinking phase,
Is
or
that
just-
thinking phase?
or a waiting for questions because you didn't hear us.
Oh, I hear you. I'm trying to think about this.
Maybe we move on, yeah. I think Alex Menon asked for, maybe you can go back to the definition of the RLCT.
Intuition comes.
Okay, I think.
Okay. We wrap up there?
Thanks, Jonathan.
Thank you.
Good night. I gotta get some sleep. Sweet RLCT dream.
How do you know this function even has any real poles?
Oh, we computed, right? Here. It's by the resolution of singularity, we computed what are the poles, right? We reduce to the situation that poles of this function will just be poles of this function. And we can do the integration, right? And the poles appear when the denominator is 0. Hello? Did you hear me?
Yeah, thank you.
Yeah, we computed. Yeah. Any other questions?
Can you go back to the definition of normal crossings?
Yeah, sure. Right, sorry, I didn't read the chat. I just saw that.
That's fine.
Right. Oh, this post, right? We computed, right? We know where the post is sitting, right? Just for the question you asked on the chat.
So the poles are okay.
Yeah, like we want to figure out the post of this function, right?
Okay.
And then we apply the resolution of singularity, we actually compute where the poles are. It's the best.
What are the K and the H?
I'm sorry.
What are the K's and the H's?
Oh, that's from the resolution of singularities.
Okay.
After you apply the resolution of singularities, our polynomial become monomial, right? Or this K will be the exponents of that polynomial, monomial.
Okay.
Yeah, and this H also is also after you apply the resolution of singularity. This H, this
Okay, so
H
those-
come from the.
Okay, so those are just like the degrees of some monomials.
Yes,
So,
yes,
okay,
yes.
okay.
Degree of monomials. Yes.
Okay, and so the poles are at these things that that are kind of like the ratios of the degrees of monomials. Okay, I see.
Yes, we compute it. Yeah, when denominator is 0, we can compute it.
Okay.
Yeah, the whole thing just rely on this resolution of singularities, which is a very hard.
Yeah. No, I've tried to read. Oh shoot, I don't remember who the book is by, but like there's an orange book that's trying to simplify Hironaka's that I've spent some time with. So yeah, I'm familiar with how hard resolution of singularities is.
Right. Yeah. Yeah. The theory. Yeah. So
but,
yeah, let's get. Go ahead.
But can you go back to where you define normal crossings?
Yeah. Let me use this one. I think. Yeah.
Okay.
Yeah, this is a bad definition because I don't want. There is a nicer definition using like localization of rings, but I don't want to introduce that. But
Sure. Can you go back a page or two?
Mm-hmm.
Yeah. So the bottom thing right there is not a normal crossing?
Yeah, it is not.
Why not?
Yes. So the idea of normal crossing is actually the point is that around this is normal crossing if it locally looks like intersection of two straight line. The intersect transversely, intersect in this way.
Okay, so it's just the fact that it's the three straight lines there.
Yes. So
like any like perturbation of this would turn it into like three normal crossings.
What do you mean by that? I didn't get
like
it.
I mean this is like if you replace equals 0 with equals some constant, right?
Mm-hmm.
If you like looked up or down at this for like any kind of small epsilon, then it would I think it would not then it would not be all of those would not be at the origin. You'd have like three things that were near the origin instead, right? Like if you can just kind of imagine moving any one of those lines a little bit, and you'd end up with like three normal crossings instead of a single, non-normal crossing, right?
I didn't get that picture.
If you equate that to something not 0, then you change the entire level set.
Yeah. But it's a pretty small change in the level set, right? And so, and I think it's very likely that like that new thing just looks like this with that kind of shifted so that you actually just have three normal crossings instead of one terrible crossing.
I think if you
does that seem plausible at least? I mean, even if it's not definite.
If you change, like you're talking about the bottom equation, right?
Yeah.
So the bottommost equation, if you set it to equal to something else, the chances are the level set is not even singular.
No.
It
would. If you just change it instead of 0, if you change it by like plus or minus epsilon,
yeah,
then it'll still be singular.
It won't, right? Because
yeah,
the set of single level set is actually measure 0.
But like what's like a small perturbation of this picture that would what's a small perturbation of this picture that would make it not singular? Like it looks like it's going to have to self-intersect, right?
like
Oh, does it? But oh no, okay, no. I guess it could turn into like a hyperbola on bottom and like two kind of ellipsoidish things on the left and
Yeah.
right, something like that. Okay,
Yes.
okay, sure. Okay.
Yeah, exactly.
yeah.
Okay.
Yeah, and you also think about you add one more parameter here. Just let this equal to a. You let it vary. It only, I think, only at a equal to 0 you have a singularity.
Yeah.
Yeah.
I forgot whether it is for this case, but there might be multiple A's where it is singular,
No,
but those A's are finite.
No. That's definitely not true, right? Like think about like elliptic curves, right? If you have an elliptic curve that's intersecting itself, then you can get like a pretty wide parameterization of elliptic curves with a self-intersection.
Oh,
Right? Like
yeah, you're right. Yeah. I was
yeah.
more thinking like, yeah, it is measure 0, but then measure 0 doesn't mean discrete. Sorry.
Yeah. And so I think that it's very possible that like if you made this like plus or minus epsilon, then you'd still have something singular there, right?
Yeah. For this, I'm not sure for this example.
Yeah, me too.
Yeah. For this example, then we'd have to actually like do calculations, and we don't want to do those right now. But
yeah.
Okay, can you go forward to the definition? I think. I guess I'm not understanding. No, because that seems like it should still be a normal crossing thing, right? Because you're not restricting it to just like two things. You've got like 1 through D, right? So it seems
yes,
like
I
you
want
could
to
get
correct that. Normal crossing doesn't mean that like in 2D you are only allowed 2 crossing. You can have three lines, multiple lines crossing, but they need to be in certain forms. Yeah.
So
actually, is that true?
So isn't the last one still normal crossing then? Because like it's it's
in R2 the normal crossing has to be like look like intersection of just two lines.
Yes. I think Zhongtian is right. I was wrong. Yeah.
Because in R2 when D equal to 2, everything will just be because we only have 2 variables, right? Some constant here.
Oh, I see.
Everything will.
The D is showing up in 2 places.
Yes.
Okay, I see. Okay. I see. Okay, yes. I believe you now. I believe you. Okay. Okay, that makes sense. So something, Zhongtian, something that I think would take a lot of effort on your part, but I would find very, very valuable, and I bet other people at the workshop might also find valuable if you did, would be if you like teched up a couple of the examples in this as problems to do, and sort of said like, here's the definitions, like as an exercise, try and do this, and then just like gave exactly the same problem that you went through as an example that we could just like try and do, try and replicate ourselves.
Right. Yeah.
I know that's a lot of work. So if you don't have time, then that's fine. But like I think that could be very, very useful.
Yeah.
So
I'll try to do that. Yeah. Yes.
Okay.
I'll try to do that. Yeah. Also, like, because I think it will be even at this stage, it will be helpful because for the last example, I didn't really go into the details, and then you maybe the thing you want to try is just to compute the RLCT of the last example, do a bunch of blowups. That might help. I'll try to like take up latex, all these things.
That would be that would definitely be good. And I mean possibly also include like enough definitions that it could just be self-contained for people who didn't watch the lecture or anything.
Yes, sure.
Okay. Well, thank you very, very much. I thought this was a very good lecture on very difficult material. So thank you. Appreciate it.
Thank you. Yeah, no worries.
Yeah, thank you, Zhongtian. I might need to kick everyone out now.
Yeah, sure.
Oh yeah, Nathaniel, regarding your question. Oh, he's gone. Okay, cool. All right. See you, Zhongtian. Thanks for the lecture.
See you. No worries. See you. So tired.
Yeah.
Yeah, going to sleep. See you.
More.